Welcome to LabMinutes.com and our lab video series on MPLS. You can find a complete list of MPLS videos on our website by clicking on the link above and sign up for our newsletters to receive the latest video updates. MPLS is a label switching technology that instead of relying on IP addresses in the IP header to route packets, the router actually builds a label switching path, or LSP, for packets that requires the same forwarding treatment, and this is also known as a forwarding equivalence class, or FEC. And this includes things like source destination IPs and IP precedents. And then the packet will get switched based on the MPLS label that the packet carries, while the MPLS label itself are swapped along the way until the packet reaches the last MPLS router closest to the destination. But before the packet label switching can happen, the router needs to know what label to use, and that is through a label distribution protocol, or LDP. So at the high level, a router allocates local labels to routes that it have in the routing table and exchange those labels with its LDP neighbors to complete the label switching path. And there's actually a lot more detail that goes underneath of the protocols and how labels are actually distributed. And you can find those information at Cisco docs, so we won't go into detail in this video. Since LDP is a fundamental component of MPLS, our first video in our MPLS video series starts with looking at LDP and its configuration. So in this video, we're going to be looking at LDP, and this includes the LDP label exchange and how that actually happens, and the binding table that contains all the labels, whether it's local or remote label as received from the neighbors. And then we're going to look deep into the packet of LDP and see what that looks like. Now for our network topology, here's our physical topology, and since this is the first video, let's spend a little bit of time trying to familiarize ourselves with what we have here. So we have 8 routers altogether, R1 through R8, with R2, R3, R4, and R5 connected in almost a full mesh, but not quite, since we're missing the link here between R2 and R3, and these are our point-to-point serial link. While the other connections that we have here are just connected over VLANs. And also at the top, we also have a switch 1 that's actually the same switch that provides all the layer 2 VLAN connectivity. But as far as this layer 3 is concerned, it has SPI of 104 that is connected to router 4. Okay, so this is pretty much the physical topology that we're going to be using throughout our MPLS video series. We might later on in the future lab add additional links here and there, but this is pretty much it. And the majority of the links will remain the same. Okay, so scrolling down, here's our layer 3 topology. And here in the middle, among R1, R2, R3, R4, and R5, we're going to be configuring an MPLS enable network. As you can see, we already have the link label with LDP protocols. And just for this lab, we already have a EAGRP AS10 configured on all of these devices. To provide network reachability, each of these routers has a list of loopbacks right here, loopback 0, with the IP 172.16.0.x, with the x being a router number. While all of these routers also have loopback 10 through 12 configured in this format. In this lab, we only have the loopback 10 through 12 on the edge devices advertised into EAGRP, and these are R6, R7, R8, and our switch 1. And we're going to be using those interfaces to test our connectivity across our MPLS network here in the middle. And as a quick reminder, all of these lab diagrams and documents will be made available for download on the video page on our website, so I encourage you guys to download those and have them printed out in front of you as you follow along our lab as we perform the configuration, just to make things a little bit easier, since we're going to be dealing with a lot of interfaces here. Okay, so now let's go ahead and start with our configuration and task number 1 with LDP. So we need to enable LDP on links that connects our 1, 2, 3, 4, and 5, and then we're going to have to source all of our LDP sessions from loopback 0. Okay, going back to our diagram, this is the layer 3 topology again, and you can see all these links with the LDP label. So these are the links that we're going to be configuring LDP. You can see that stays within our little circle of MPLS enabled network. Starting off with our router R1 on FAST00 interface. So to configure MPLS or enable LDP, first we need to make sure that IPsec is enabled. That's almost required for the configuration. And to enable MPLS, you do MPLS IP command, and then followed by MPLS label protocol. As you can see with the question mark, there's actually 2 types of label exchange protocol that you can use. TDP, which is the predecessors of LDP, and that was a Cisco proprietary, and now LDP has become a standard. So here we use LDP, but as you can see in parentheses, it's a default anyway. So that command is actually not necessary. And then in order to specify the source of a loopback, we use the command MPLS LDP, router ID, loopback 0. If you question mark, there's also an additional option of force, and this is used when you're trying to change the router ID when you already have the LDP adjacency already established and you want to force the connection to go down right away and then start using the router ID. Although since we haven't really configured LDP, force option is not really necessary, but you can also put that in anyway. Okay, so either way it doesn't hurt. And then to enable LDP on the interface, we go under the interface fast00 and then MPLS IP command. Okay, see if we can do a show MPLS LDP discovery. So right now it's only transmit and it hasn't received anything as far as the LDP discovery message. Okay, so from R1 we're gonna jump over to R3, just gonna go from left to right. So on R3 we have two serial interface and fast00. Same thing IPsef. Now that we have done this once, we're just gonna go a little faster here. So protocol LDP, router ID, loopback 0, forgot LDP, router ID, loopback 0, force, interface fast00, MPLS IP. Let's make sure we get all the interfaces on this. So we have 000, MPLS IP, and then serial 010, MPLS IP. Okay, next router is router 4. We have three serial interfaces, 01, 02, and 00. So going over to router 4, IPsef, label protocol LDP, router ID, loopback 0, force, interface 000:0, MPLS IP, 01, and then 02. Okay, you can see that we have a adjacency that came up with router R3. Alright, now we've done with R4, we're moving over to R5, and R5 also has three serial interfaces. See router R5, IPsef, MPLS IP, MPLS label, protocol, LDP, MPLS, LDP, router ID, loopback 0, so you can do force, and then interface 000, 0, PLS IP, 01, and then 02. Alright, we'll come back and check on these neighbor adjacency in a little bit once we complete our configuration. Now over to R2. And R2 has two serial interfaces, 000, 010. IPsef, IP, label protocol LDP, router ID, loopback 0, force, 000, PLS IP, 010, MPLS IP. Okay, now let's go back to, let's say, R3, since R3 is going to have the neighbor of R1, R4, and R5. So we should be able to see all three neighbors. Start with the show command, show MPLS interface. You can specify the interface that you want to look at. So let's look at fast00, which is where R1 is located. Detail, and here you can see the label, the IP labeling is enabled with LDP command. There's no LSP tunnel. BGP labeling is not enabled, and MPLS is operational with the MTU of 1500. Okay, now if we do show MPLS LDP discovery, and this is just telling you whether or not the router is receiving a discovery multicast packet from the neighbor, because by default the router is actually saying hello message just like any other routing protocols, and that's in the form of a multicast packet. So you will see when we do the packet captures to the well-known multicast IP of all router, which is 224.0.0.2. And since all of these three interfaces or neighbors are marked as received, that means the R3 has actually been receiving a hello packet or discovery packets from all of these three interfaces. And you can see it also has the router or RDP ID on each of these. So that's R1, R4, and R5. Okay, as long as we are seeing both transmit and receive, we know that the routers are seeing each other. But just to verify the states or status of the LDP session, which is for the label exchange, and that is in the form of TCP connection, we need to do a show MPLS LDP neighbor command. You can see here we have 3 peers. So R3 has currently LDP connection to R1, R4, and R5, which is all that we need. So let's take a look at the connection to R1. So the peer ID is 0.1, which is the loopback 0 of R1, and then itself local ID is 0.3. And you can see right here TCP connections. And by default, it's using the router ID to build that TCP connection. And you can see LDP use TCP port 646. Okay, here you can see the message sent received, a little bit of a stats here, and as well as the uptimes. It's been up for 5 minutes. This also has the discovery source. So this is the IP that sourced the multicast discovery from the neighbor. And the R1 use its physical interface IP fast00, which is 13.1 as the source of that. And some of the additional information that's been sent from R1 includes all of its interfaces that are currently configured on R1. So this way R3 knows exactly what IP belongs to R1, although some of these interfaces are not really relevant. For example, these are the loopback 10 through 12 of R1, although we don't even have those advertised in now EIGRP. It came along as part of the LDP session. And then we see similar information for R4 with the TCP connection built using the router IDs as well as the R5. Okay, so the most important thing here is we need to make sure that the router ID that you specify when you configure the LDP are reachable by the routers. So here we are, since we're sourcing from loopback 0, and we already have loopback 0 advertised in the EIGRP, we're not having any issue here. But just to see what happened, let's say on R1, if you take away the loopback 0 advertisement from EIGRP, so let's say that we no longer want to or stop advertising the loopback 0. So let's do no network 1601. Just want to show you that this can create an issue. So delete that, and then we can clear MPLS LDP neighbor just to bounce the session. And now we can see what happens on R3. You can see that the connection is not coming back up. If you do R3, R3 is no longer has a route to R1 loopback 0. And if you do show MPLS LDP discovery, you can see right here, although it's been receiving a discovery of multicast hello packets from R1, it claims that it has no route, or it doesn't know how to get to the R1 LDP router ID, which is the loopback 01. And since R3 has no way to build a connection or LDP connection with R1, we do show MPLS LDP neighbor. You can see that we do not have a neighbor adjacency or a peer connection with R1 for that reason. Okay, and that's because by default LDP uses the router ID as a transport IP to build the TCP session. Okay, so now let's go ahead and put that back. EIGRP 10 network 01. Alright, so you can see the LDP neighbor comes right back up. And we should also have right here the LDP session. Okay, so that's for R3, and let's do a quick check on R2 as well, though we're not going to go through all of the routers right now. So show MPLS LDP neighbor, and R2 should have a adjacency with R4 and R5. Okay, so that looks good. Now, moving on to our next task, which is we're going to go through and review LDP binding tables and MPLS forwarding table just to get a better understanding what's actually contained in those tables and how the labels are actually used. So let's start off again at R3. We can do show MPLS LDP binding. So these are all of the labels that R3 currently knows of. They're both local. So you can see local binding being the label that's been allocated by R3 itself to each of the routes that it has in this unicast routing table, as well as the remote binding, which is the labels that's been received from its LDP neighbors. You can see right here, for example, in R3 or R4, right here, loopback interface 0.4, it has a label that's received from R1, R4, and R5 of 30 imnull. And we'll talk about implicit null a little bit later and what it's actually used for. And we also have a label, for example, 25 that's being learned from router R5. And you can see, interesting enough, which is R3, its own loopback 0, it also receiving a label for those from its neighbor. Okay, so this particular command just gives you the complete pictures of all the labels that R3 has, since it's the binding table. Then we can also, if you just want to look at the local label that's generated by R3, we can specify the command local. You can see all these are the local labels. And these are the label that's being advertised to its neighbors. If you notice right here, some of the routes that's local to R3 use a label which is a special label called implicit null. And what it does is when its neighbor receives this particular label for the routes, if the neighbor router has a packets that's being sent to this particular routes, it will basically tells that neighbor router to strip off the topmost MPLS label. And this is what is known as promoted hop popping, or PHP. And that way it saves the destination router the label lookup, and let's just go ahead and do the IP routing. Since these are the local routes, and that's just the default behavior. And there's going to be some scenarios where you do not want to do imnull, as once the MPLS label has been stripped off, you lose certain information that contains the MPLS label header, which is the experimental bit when you do the QoS. So there's occasions where you might not want to do that. Okay, now in addition to the binding local command, we can also do a remote label. So if you want to look up all the label that's being learned by your neighbor, but you need to know the exact label that you want to look up. For example, let's pick one right here, 30. So you can see the same label, number 30, is being learned from multiple neighbors, and it's actually being used for different FEC or the subnet or the routes. Okay, but if you want to look at the labels learned from a particular neighbor, you can do show MPLS LDP binding, and then you specify the neighbor. Let's say we want to look at all the labels being learned from router R1, so we specify the router ID of R1, which is 0.1. As you can see, all these right here, and these are all the labels that R1 has sent to R3. Okay, so far by looking at this binding table, it might not give you a whole lot of meaning of how the packet switching actually works. But if you do a show MPLS forwarding command, it might put things into perspective for you. So right here, these are the forwarding table is the table that the router used to switch the packets. So what it means right here, local label, is the label that the router expects the packets, inbound packets or incoming packets, to contain. So based on the label on the incoming packets, the router knows exactly what's the label that the router has to swap to, and these are the outgoing label, and it knows exactly what's the prefix that's going towards and what is the outgoing interface as well as the next hop. Okay, so you can see right here the local labels has to be unique. So you can see you don't really see a duplicate label number here, as opposed to the outgoing label that you might see some duplicates on the outgoing because it's coming from different routers. So this table right here tells you exactly how the label is going to be treated as it comes into the router. And the majority of the packets will get swapped on the labels, but you can see also that there's some of the FEC that will pop the label or remove the label. And when you say pop label, it means the topmost label. So it doesn't, if the packet contains multiple labels, then it's just going to be a topmost. It doesn't completely remove the label from the packet. And when you see the pop label, usually it means that the next hop is going to be a last switching routers in the switching path for that particular FEC. Okay, and the pop label is a result of the implicit null label that it receives from the neighbor that we talked about right here. Okay, so if you locate 172.16.18, we are receiving an implicit null from router R1, and you can see right here, implicit now get translated to pop label, and the next tab is 13.1, which is R1 fast 00 interface. Okay, just to give you even more detail of the forwarding table, you can specify the detail option. And here, in addition to the in-out labels, you also see a encapsulation information. The MRU, which we will talk about in the next video, that stands for maximum receive unit, and it also tells you exactly the label stack information, which is what's the MPLS label that's going to be imposed on the packet as it leaves the router. Okay, so since we're only dealing with one label here, so you can see outgoing label is 16. It's clear it gets translated to label stack of 16, but later on when we deal with the MPLS VPN, we might be dealing with more than just one label. For the most part, MPLS VPN will be 2 labels, and it will show up right here as well. Okay, so these are pretty much the most common shell commands that you'll be using when configuring or dealing with MPLS.